Okay, this is part 2 of the second video for the portion of the midterm project where the skier's in the air jumping, like this part. So we need to start with our free body diagram. And in this case, in the first part we had our coordinate axis aligned along the incline. In this part, we're going to have just our, sort of a vertical and horizontal coordinate system. So this is X, and that is Y. Okay, so in this case, we have, of course, gravity still going down. Okay, so, we can imagine, let's say, just to have a visual kind of what's happening here, let's say our skier is like this. And, well, I probably should have done it the other way, right? Because they really tuck forward in this part. And let's say the motion is in this direction. So that's the direction of the velocity at that point. Okay, so let's just sketch that over here. So say, this is our direction of motion, for example. So drag will always be opposing motion, so that's our drag force. And then once the skier is airborne, we have a lift force as well, and that's going to be perpendicular to drag. So that's the force of lift. And we define this angle phi as the angle between the horizontal x-axis and our direction of motion. So this is going to change, right? Phi changes throughout as our, ski jumper moves this way, and then lands back down on the ground somewhere. The direction of motion is the velocity vector at each point, which is really like the tangent to the trajectory. So that's going to be changing as we move through the flight. But we'll just always characterize this angle phi as the direction between the horizontal and the velocity. Okay, so we'll do our force analysis again, but we need to break our lift and drag into their components. So drag has an x component that looks like, maybe I'll just do it separate so we don't have too much overlap here. Get confusing. So drag is down like that. And again, if I just kind of, like that is phi. So this angle in here is phi as well. Just by some kind of, I don't know what they are. They're the same angle. Let me know if you know the geometry rule. Okay, so this is our drag in the x and drag in the y. Okay, now lift is going to be perpendicular to that. So let's just see where theta ends up inside the lift triangle. So lift will be up at this angle. Okay. And then we have that kind of perpendicular for drag. This angle in here is phi. So this angle here is 90 minus phi because these are perpendicular. So then in here, inside that lift triangle is where phi is. So we have a y component of lift that'll be the adjacent f of y, and then the x component is the opposite side. F lift x is going to be f lift sine phi, and f lift y is f lift cos phi. On this drag triangle, x is the adjacent side, so this is f drag cos phi, and the y component will be f drag sine phi. So we kind of have the opposite trig functions for the lift and drag. So let's apply Newton's second law. Sum of the forces is mass times acceleration. Again, these are all force vectors, so we got to think about direction. So we'll put in a column vector for each one, force, 3 forces. Okay, and that will equal max and may. So this will be our x and y component, and we'll have gravity, the drag force, and the lift force. Gravity is totally in the y direction, so 0 in the x minus mg in the y. Drag, we have negative f dx, so So ft cos theta, or phi, sorry, and then minus ft sine phi. And then for the lift, we have negative in the x, so negative FL sine phi, and then we have plus FL cos phi. So the lift right in the y direction lifts the object up, or lifts the sphere up. Okay, so we want to solve for our acceleration. So let's look at the x direction first. So we have minus ft cos phi minus FL sine phi equals max. So the drag force we saw in part 1, so we're going to say that's minus b d v squared. And in the x direct, yeah, so v squared, right? And then we have the cosine phi. So that's v cos phi. And this is actually our x velocity. So, right, because that phi is actually defined by the velocity vector. Okay. Okay, and then we have minus the force of the lift. So lift is going to be very similar, but b sub L, v squared sine phi. And again, that's BL. So again, v sine phi is our y component. And that equals max. So we want to solve for that. We divide every term through by m. So ax equals negative the drag coefficient over the mass, vy, minus the lift coefficient over the mass. Oh, what did I do wrong here? That's vx. Sorry about that. vy. Okay. And then we can get a similar relationship for the y direction. I'm just going to skip a few steps, but you should not do that. You should write these out when you are rewriting this force analysis. So ft sine phi plus FL cos phi equals may. Okay, sine phi, so this is going to be minus b drag v squared sine phi, and this is going to be v sine phi is the same as vy. And then here we have the drag v squared cos phi, and that's going to be bl vx, and we get still our minus mg equals may. Divide through by our mass, and we get ay is minus g minus bd over m vy plus bl over m vx. Okay, so that gives us our x and y accelerations during the flight part of the jump.